Hey guys and gals, welcome to the next to last video / lesson for Unit 3 of Algebra 1. It's a pretty short unit because we're kind of hitting some big concepts in this unit, and then we're going to really put some details on that, and we're going to hit that with some all kinds of different problem types and different details and other things in the next unit. And so in this video, in this lesson, we're going to talk about rate of change and slope. We're still talking about linear functions, but this time we're talking about how slanted are they. So rate of change is, in really simple terms, rate of change is how fast something is changing, right? So how fast it's changing. Now, so if we're looking at a linear function like this, we're basically talking about how steep is it from pictures, and we'll talk more about that in the next unit, right? So is it very steep, or is it a little steep, or is it not very steep at all, right? So rate of change has another name for it, especially when we're talking about linear functions. Rate of change has a simpler name, which is nice because we have less writing to do. So rate of change, how fast a linear function is changing, is also called slope. The slope of a linear function. Now, what is the slope? First thing we're going to The first thing we're going to do, so we don't have to even write that much, is we use a letter for slope. We use the letter M for slope. So slope equals M. Slope equals rate of change equals M. So far, so bueno, right? It's always a fraction. It is a ratio of the change in y to the, or over, the change in x. Okay, so let's see if we can figure out what that means by doing an example. Example 1. We are going to use the table. Don't worry, we'll draw a table. Use the table to find the rate of change. Then explain its meaning. I'm just going to put explain. Does that work for you guys? Good. I'm glad it does. Thank you. Thank you very much. So here's our table. On the X side of the table, we've got the number of computer games. Probably should say video games, but that's all right. Excuse me. Number of computer games. And then on the Y side of the table, we have the total cost. Which is in dollars. Okay. And then let's say we'll go ahead and label this as the X and this is the Y. So then we're going to fill in the table. We have 278. We have 3 LOL JK, for 156. And, oh, I'm hitting the wrong button. And 6 and 254. Now, we're going to look at it in a minute, some things, and we can determine from a picture like this whether the graph is, in fact, a linear function or not. But this one, we're just going to assume that it's a linear function, and we're not going to stress too hard about that. So we're going to just, in order to do this, to find the rate of change. Rate of change is the difference of the y's over the difference of the x's, right? And so since we know it's a linear function, since I'm telling you it is, all we have to do to find the rate of change is we've got to subtract the y's over subtracting a couple x's. So we just got to pick two of these points. We've got point number 1, point number 2, point number 3, right? So let's pick two. So let's pick this one and this one. So we're going to put y's on the top. So 156. And then we're going to subtract this one over the y's on the bottom. 4 minus 2. So 156 minus 78 is 78. I don't know why I had to look at that. I should have known what that was going to be. It's getting late and my head's foggy and all the things. Over 2. Right? And then we can reduce this fraction to 39 over 1. So the rate of change is 39 over 1. Right? That's part of the answer. Now we got to explain what it means. So what that means is that every game cost, in whatever hypothetical situation this is, right? $39. For every one game, they paid $39. There you go. Let's look at something else. Let's look at, we're going to do like 2 more examples. We're going to do 3 or 4 more examples, or we're going to do 2 more examples of the same type. So the instructions are going to be the same on both of these examples, and that is determine, this is what I was alluding to earlier, determine whether each table represents a linear function or not. Okay. So I'm going to put example 2 and example 3 on the same page so we can compare them. All right, so for example 2, we're going to have a T-chart table. And for example 3, we're going to have another T-chart table. Okay, so in this example, we're going to have the values 1, 4, 7, 10, and 13 for X. That's the domain of this guy. 1, 4, 7, 10, 13. The range of this guy is going to be -6, -8, -10, -12, -14. So then, for example, 3, the domain is going to be -3, excuse me, -1, 1, 3, 5. And the range of this function is going to be 10, 12, 16, 18, 22. Now, so in order to determine whether each one of these is a linear function or not, we've got to compare the slopes or the rate of changes, right? And so what we're going to do is we're going to figure out the difference, and we're going to kind of walk these on down. And we're going to do this by subtracting the x's and subtracting the y's. So 4 minus 1 is +3, right? You see what I'm saying? So we just subtract this one, the final minus the initial, the bigger one minus the smaller one. 7 minus 4 is +3. 10 minus 7 is +3. 13 minus 10 is +3. So that's consistent so far, right? And then -8 minus -6 is -2. -10 minus -8 is -2. In case you're confused on these, that's why I stuttered, because I was thinking about whether to explain this or not. In case you're confused, let me jot one of these down. -8 minus -6. So we ka-chink, ka-chink, and it's -8 plus 6. We subtract and keep the sign of the bigger one, hence the -2. So in case you were confused about where, though, that number came from, there it is. Want to make sure we're good to go. G to G on that. So it's -2 again right here, and the -14 minus -12 is -2. Also consistent, okay? So this one is -1 minus -3, which would be a +2. This is 1 minus -1, which is also +2. That one, you might have something fuzzy in your head. 1 minus -1, ka-chink, ka-chink, equals +2, or plus squiggle, almost Z lightning bolt, whatever that is. You get the point, I think, probably. Let me know in the comments if you don't. 3 minus 1 is +2. 5 minus 3 is +2. Now, 12 minus 10 is +2. 16 minus 12 is +4. 18 minus 6 is +4. 22 minus 8 is +4. Okay. So, if you haven't guessed by now, this one is linear. This one is not linear. Okay. And what's important to note here is that the ratio, oops, that was not what I wanted to do. Try again. There we go. Is that the ratios are the same. Because see, here we have 2/3. Here we have 2/3. Here we have 2/3. And then finally we have 2/3. Oops. So the ratio is the same all the way down, which is what tells us that it's linear. If the ratio of the difference of the y's to the difference of the x's is always the same, then it's linear. So this one, I don't even have to walk through all the way, right? This one is 2/2, which is 1. And this one is 4/2, which is 2. So we don't even have to go any further. It's going to be 4/2 and 4/2, right? But this one breaks it, makes it not linear, because the ratio, that slope, is not consistent all the way down. So that makes it not linear. All right, so the last thing we're going to do, which we actually kind of already have seen, we're just going to make sure we see it in another form. That way we're clear and we got things good to go. So example, whatever this is, example 4, yes. Example 4 is going to be find the slope between -2, 0 and 1, 5. So we've already seen this, actually. We saw this on a previous problem. So to find the slope, we're going to use what we're now going to call the slope formula. We wrote it down earlier, but we're going to officially call it the slope formula now. And that is m, remember we use the letter m for slope, equals y2, the second y, minus y1 over x2 minus x1. The difference of the y's over the difference of the x's. That's all we're talking about. If you're having trouble, I might note a really common acronym for remembering, a way to remember which goes on top and that y goes on top and x goes on the bottom, is we think about rise over run. Rise over run. And it's rise over run because you got to rise before you can run, right? So that can help us because rise is the y up and down, right? And run would be the left and right. Makes sense? I hope so. Okay. So we've got our points. We've got our formula. Let's plug it in and use it. So we're going to almost treat this like it's a substitution problem, right? We're going to put parentheses everywhere a variable is in our formula. And then we're going to substitute numbers in there. So y2 would be 5. Points go x, y, right? Y1 would be 0. X2 would be 1. X1 would be -2. Okay. So this equals 5 minus 0 is 5. 2 minus -1, we've got a ka-chink, ka-chink. So it ends up being 1 plus 2 over 3. Now, for our slope, instead of converting to a mixed number or decimal, we want to leave this as a improper fraction because it's going to be easier to graph from later. We'll talk about that a lot more in the next unit. But for slope, we leave it as an improper fraction. Let's do one more quick example like this. We won't even write out all the stuff. We'll just write the 2 points we're finding the slope between to illustrate something interesting, right? So the 2 points we're going to find the slope between are -2, 4, and -2, -3. So the slope formula is m equals y2 minus y1 over x2 minus x1. Going to plug in our numbers, right? Okay. So we're going to put a -3 right here, a 4 right here, a -2 right here, and a -2 right here. So the top one, -3 minus 4, signs are the same, so we add and keep the sign. -7 over -2 minus -2, ka-chink, ka-chink. -2 plus 2 is 0. We can't divide by 0. Can't happen. So this slope is undefined. What that tells us, just worth noting, we'll see some examples of this in the next unit and stuff, is that this line, whoops, is a straight up and down line. So this line looks like that right there. We'll talk more about that in the next unit. That's it for this video. We've got one more lesson in this unit. We'll see you in that video. Thank you for joining us. If you're one of my students, do your homework. We'll see you in class, all the things. If you're not one of my students, then thanks for joining us. Let us know in the comments whether these videos have been helpful to you and what other things you have questions about in math and all of those things. If you want to check out what else we're doing, you can go to emberlearninglabs.com. Also, we are offering this entire Algebra 1 video series, all the lectures from our Algebra 1 course for free here on YouTube. Because of that, it would be really helpful if you hit that subscribe button and dropped a like, or just do that anyway. Hopefully these are useful. That is our goal. Thank you guys. Have a great day. Bye-bye.